This is a recording for section 14.3, Hamilton paths and Hamilton circuits. You might hear me call them sometimes Hamiltonian. You can use either word. I kind of grew up with Hamiltonian, but the book uses Hamilton, so I might slip and say that. In the last section, we talked about Euler paths and Euler circuits, and remember those were, can we trace the graph crossing each edge exactly one time? And with Hamilton, we will look at vertices. So question here, when is it possible to find a route along distinct edges of a graph that visits each vertex exactly once? And so if we do that, that is going to be either a Hamilton path or circuit. So instead of tracing each edge, we're going to want to go around and hit each vertex exactly once. And if it was a circuit, of course, we would close it. So a path that passes through each vertex of a graph exactly once is called a Hamilton path. If a Hamilton path begins and ends at the same vertex and passes through all the other vertices, it's called a Hamilton circuit. So remember, note here, Euler path has to do with visiting each edge exactly once, and Hamilton path circuit has to do with visiting each vertex exactly once. And we will talk about in a minute, this is often called the traveling salesman problem, right? Wants to hit all these cities or towns, right, exactly one time. So part A here, for this given graph, it says find a Hamilton path for the graph, and basically you could kind of start at any vertex that you want. You know, there's many different answers. And start at any vertex, since it doesn't start at any vertex since it doesn't indicate anything. So I'll just start here at A. Again, so we want to hit each vertex exactly once. You can only go to a vertex, of course, if there's an edge there. So we can go from A to B to E. Anywhere you want to go. There's so many of these, to C and back to D. And we want a path, not a circuit. We've hit each vertex exactly once, so we're done. We're not going to close it. The second part B, says find a Hamilton circuit that starts at A, so we could actually write the same thing down, but then we would close it. A, B, E, C, D, but then we would have to go back to A to be a circuit, right, to close it. So and again, you will not be hitting each edge exactly once, only each vertex. Find a Hamilton circuit that starts with vertex C. A circuit, so we want to start at C and end at C, and again, there's a bunch of different possibilities here. C, D, E, A, B, C is one possibility. A complete graph is a graph that has an edge between each pair of vertices. Are the following complete? Why or why not? All right, and if we look at part A here, it's not complete because there's not an edge between A and D or B and C. Here it is complete because there's an edge between each vertice and every other. So a complete graph, again, is one where there's an edge between each set of vertices. The number of Hamilton circuits in a complete graph. So let's first look at a complete graph on 5 vertices. And that's in this picture, and you usually denote that case of 5 like that to mean a complete graph on 5 vertices. If a vertex, so let's just start here, okay? And if we start here and we want to, again, we want to know how many Hamilton circuits are there? How many ways can I go through the vertices starting and ending at one vertex? How many different ways can we do that? And you're going to see why when we start looking at weighted graphs, why we even want to do this. But if we start at this one, we can see that there's actually 4 different paths that we could take. So let's start here at A, we'll call that A, and we could go to 4 different vertices. Then suppose I end up taking this path and I go to this vertex. Now from there, I'm not going to go back to A, right? We visit each vertex exactly once. I have 3 choices of where to go next. And then suppose I go to this vertex. We'll call that C. Well, I'm not going to go back to B and I'm not going to go back to A, because if I go back to A, I've closed the circuit too early and I haven't hit the other vertices. So I only actually have 2 possibilities of where I could go to next. And then suppose I go down here. Then I only have 1 choice because I can't go back to A, it would close it too early. Same thing with B. And I just came from C, you would have to go to this one over here. All right, there's only 1 choice of where to go. All right, and then of course you close it up. So if you want to do times another 1, that's fine. But this is the fundamental counting principle, means that the number of possibilities, you would multiply these together. We talk about the fundamental counting principle in chapter 11, which may come after this, but you probably remember from high school or elementary school when you were trying to figure out how many possible outfits that you could have. If you had 4 shirts and 3 pairs of pants, you would do 4 times 3 is 12. So here, if you have 4 possibilities and 3 possibilities and 2, you would multiply them together. And that is listed right here. That asterisk there means multiplication. So that the number of Hamilton circuits is 4 times 3 times 2 times 1, which is 24 Hamilton circuits. So the number, and if you notice that was 5 vertices, then we did 4 times 3 times 2 times 1. So the number of Hamilton circuits in a complete graph with n vertices is n minus 1 factorial. This factorial, in case you haven't seen it, it's often used in probability. So this exclamation mark is read factorial. And what it means is 7 factorial means you do 7 times 6 times 5 times 4 times 3 times 2 times 1. 4 factorial is 4 times 3 times 2 times 1. But if you notice, when there were a complete graph on 5 vertices, had 4 times 3 times 2 times 1. So you do n minus 1 factorial. Example, how many Hamilton circuits on a complete graph with 6 vertices? So we do 6 minus 1 to get 5, and we do 5 factorial. Not 6 factorial, because with 6 vertices, we only have 5 others to go to with the starting vertex. 5 times 4 times 3 times 2 times 1, which will give you 20 times 3 is 60 times 2 is 180 times 1 is 180 or I meant 120. 60 times 2 is 120. So you always just take 1 less than the number of vertices and then do the factorial. And if you can just punch that in a calculator, you don't have to use the factorial button, and most scientific calculators don't have one. That just reminds me, again, you should be doing your homework with a scientific calculator, and the one that's recommended on the syllabus is that TI 30X11S. You do not want to be using a graphing calculator on your homework because you can't use it on the tests. You want to use one, get familiar with where buttons are on the one you can use for the test. The number of Hamilton circuits in a complete graph. So any circuits that pass through the same vertices in the same order will be considered as the same, right? We don't want to have to list out 25 different Hamilton circuits if many of them are the same. For example, if I start with A and I make the circuit A, B, C, D, A, that is going to be the same as starting at B and going in the same direction. So I went the same B, C, D, A, B. Okay, these are the same circuit. So to avoid duplication, we will start our list of circuits always beginning with the same vertex, because you're going to see why we are going to want to list out the possible circuits actually later on in this section. So let's just choose one vertex to start with, and traditionally you just start with A and then just list those out. So list all Hamilton circuits for the following graph. First, you should decide how many circuits there should be. So you know that you have the same, all of them. You could start with any vertex since it isn't given. So let's start with A. So again, we'll start with A. And first we want to determine how many there are. Remember that there's n minus 1 factorial, and n is the number of vertices, and this one has A, B, C, and D, so that's 4 vertices. 4 minus 1 factorial, which is 3 factorial, and 3 factorial means 3 times 2 times 1, so that's 6 times 1, so there's 6 Hamilton circuits. So we will know that we have found them all if we get 6. So we're going to start with A, and probably the one that jumps out is first is to go A, B, C, D, and back to A. Right? A, B, C, D, and back to A. Now how I start listing them is obviously A is going to be starting and ending, right? So basically we just need to figure out the different combinations of B, C, and D. This is a complete graph, right? You can go from each vertex to every other, so it is a complete graph. So let's start, so we started with AB. Then I kind of like to fix that AB. I could go AB, C, D, or I could go AB, D, C, A, since it's a complete graph. So I sort of fix the first two, AB, and then you just have CD or DC. Then I would next go, since those are the only ones that are going to start with AB, because all of them end in A, right? So A, and then go to C next. All right, so we did all the ones that started with AB. So with AC, I can either do AC BD or AC DB. Those are the only choices that start with AC. And then, of course, we put the end at the A to close the circuit, or put the A at the end to close the circuits. But those are the ones that start with AC. So then you know that you would start the next one with AD. You can do AD, and then what's left is B and C, ADBC, or ADCB. So those would be the ones that start with AD. And then you know you're done. You have your 6. You knew there were 6 of them. But you would know that you were done anyway, because we're only listing the ones that start with A, and then you fix the first two, A, B, and then that's all you can get. And then fix the first two again. All right, so then we know we have them all. So those are all the 6 Hamilton circuits.